Hello students, I am Mangesh Jamdhade, currently working in Maratha Vidya Prasarak Samaj S.VK.T college. In this year we are going to study the course named Atomic and Molecular Physics. So this is our first lecture in this course. In the first lecture we will get introduced with the most fundamental model of the atomic theory, which is the Bohrs model. So today we have a agenda. In this lecture we will study about postulates of Bohr's theory, and we will derive the expression for radius of Bohr's orbit. Also we will derive the expression for velocity of electron in nth Bohr's orbit, and we will derive the formula for energy of electron in nth Bohr's orbit. So today's our learning objectives will be to understand the concept of non-radiating stable orbit, and to understand discrete energy levels in the atoms, also to find the formula for radius, velocity and energy in the Bohr's theory. So let me introduce you with the Bohr's model. So Bohr's model first time introduces the concept of stable non-radiating orbits. So no other model had proposed this concept. So first time Bohr proposed this concept that electrons revolves in stable orbits which are non-radiating in nature. So he also first time introduces the concept of discrete values of angular momentum. Now classically it was known that angular momentum takes continuous values, but the revolutionary idea first time introduced by the Bohrs that angular momentum also quantized in nature. And we'll see that this model is only applicable for the hydrogen atom. So let's begin the Bohr's theory by studying its first postulate. So there are three postulates in the Bohr's theory. So we'll begin with the first postulates. So first, the statement of first postulate is that electrons revolves in a certain circular orbits around the nucleus under the action of Coulomb force. So this is the first postulate which says that electrons only revolves in certain orbits. Now here the word certain indicates that the nature of those orbits. Here the nature of the orbit is such that the orbits are non-radiating orbits in which the electron does not radiate any energy. That is, those orbits are stable orbits. Now we already know that the electron is a negatively charged particle and the nucleus have a positive charge of Ze, where Z is the atomic number of the atom. So nucleus contains Z protons and the charge on each proton is a positive charge. So the total charge on the nucleus will be Ze, and the total charge on the electron, single electron if you consider, so it is a minus E, and therefore there will be a force of attraction between positively charged nucleus and the negatively charged electron, which is given by the Coulomb's formula. So Coulomb has divided the formula to find the force between two charges. So by using that formula we get the force of attraction between nucleus and electron as F equals to 1 divided by 4 pi epsilon naught Ze square by R square. Here 1 divided by 4 pi epsilon naught is called the Coulomb's constant, and Z is the atomic number and R is the separation between electron and the nucleus. So now this is the force given by equation 1 is the necessary centripetal force for the orbital motion of the electron. So here the Coulombic force of attraction between the positively charged nucleus and negatively charged electron acts as a centripetal force necessary for circular motion of the electron, and therefore we already have the formula for centripetal force as mv square by r, where m is the mass of electron and v is its linear velocity, and therefore by equating those formula I will get mv square by r equals to 1 by 4 pi epsilon naught ZE square by R square as equation number 2. So here I have pictorially shown what is the scenario. So here you can observe that we have a total charge on the nucleus as a ZE, the separation between electron and the nucleus is R, and negatively charged electron is moving with a linear velocity v, which is a tangent shown by a tangent here. Vector v bar is a tangent to the circumference of the orbit, and that orbit is named as a Bohr's orbit. Now let's move to the second postulates of the Bohr's theory. Now second postulate states that only those circular orbits for electrons are permitted for which the angular momentum is equal to the integral multiple of h upon 2 pi. So the Bohr's second postulate predicts that you cannot take any random values for the angular momentum of the electron. The electron only take a certain values for the angular momentum which are integral multiple of h upon 2 pi, where h upon 2 pi, in this case h is a Planck's constant and h upon 2 pi is named as a reduced Planck's constant after Max Planck. Now, so according to the second postulate, we can write L bar equals to n h upon 2 pi. So n is any integer. So it says that electron take those values of angular momentum which are just integral multiple of h upon 2 pi. Now classically we already know that whenever the particle is revolving in a circular orbit of radius r with a linear velocity v and mass m, then its angular momentum is given by the formula L equals to mvr, where v is the linear velocity of electron, and by equating this we will get mvr equals to nh upon 2 pi. Now let's move to the third postulates of Bohr's theory. According to this postulate, a quantum of energy is radiated only when an electron jumps from higher energy orbit to the lower energy orbit, and the frequency of emitted radiation is proportional to the difference between two energy states. So it says that whenever the electron jumps from higher energy level to the lower energy levels, the quantum of electromagnetic radiation will be radiated, and that quantum will have an energy given by the formula h nu, where nu is the frequency of emitted radiation. That energy is given by the difference between those two energy levels in which electron jumps. So if electron jumps from initial energy level EI to the final energy level EF, here EI has a larger energy or more energy than the final EF. So the energy difference between those two levels will be EI minus EF, and those energy difference, that energy difference equals to h nu, that is the energy of a radiated quanta. This quanta is now called as a photons. Okay, so in the diagram you can see that. Now let's find the formula for radius of the nth Bohr's orbit. Now from equation 2, I have written here the equation 2, that is mv square upon r equals to 1 by 4 pi epsilon naught ZE square by r square. This equation we have written from the first postulates of Bohr's theory. So from that equation 2, I can write mv square equals to 1 by 4 pi epsilon naught ZE square by r, and so I will get m square v square equals to 1 by 4 pi epsilon naught ZME square by r as equation 6. Now in the equation 6 also, from we have equation 4, mvr equals to nh upon 2 pi, which we have written from the second postulates of Bohr's theory, and therefore I will get from this equation 4 I will get mv equals to nh upon 2 pi r, and so I will get m square v square equals to n square h square upon 4 pi square r square. So from equation 6 and 7 I can equate those two equation 6 and 7 By equating those two equations, I will get the formula for radius of the nth Bohr orbit as Rn is equal to epsilon naught n square h square upon pi z me square. This is the equation number 8. It gives us the formula to find the radius of the nth Bohr's orbit. Now equation 8, from equation 8 you can see that it indicates that the radius of the nth Bohr orbit is directly proportional to the square of n. Here n is a principal quantum number which is introduced from the quantum mechanical description of the hydrogen atom. So Rn is directly proportional to n square. So radius of the nth Bohr orbit increases as the square of the quantum number n. N takes the value from starting from 1. And so here if I substitute the values of all those constant in the expression for the radius Rn, here we have epsilon 0, which is the permittivity of free space, and its value is 8.854 into 10 raised to minus 12 coulomb square per Newton meter square, and the value of Planck's constant is 6.626 into 10 raised to minus 34 joule second. Mass of the electron approximately 9.1 into 10 raised to minus 31 kilogram. Charge on the electron E equals to 1.6 into 10 raised to minus 19 coulomb, and the atomic number for the hydrogen atom Z is equals to 1. So if I substitute those values in the expression for the radius, this value, if Rn equal to epsilon 0 n square h square pi z m square, if I substitute those values, all those constant in this expression, I will find that the radius of the nth Bohr orbit is 0.53 times n square angstrom unit, that is 0.53 n square into 10 raised to minus 10 meter. So from this expression I can directly find the radius of the nth Bohr orbit numerically. And so if I have here for example n equals to 1, then the radius of the first Bohr orbit will be R1 equals to 0.53 into 10 raised to minus 10 meter, that is 0.53 angstrom unit. For n equals to 2, I will have R2 equals to 4 times 0.53, because for n equals to 2 n square will be 4, and therefore I will get R2 equals to 2.12 into 10 raised to minus 10 meter, which comes out to be 2.12 angstrom. Now let's find the expression for the velocity of electron in a nth Bohr's orbit. So from equation 4, we have equation 4 which is written from the second postulates of the Bohr's theory. We have mvr equals to nh upon 2 pi, and by taking v and r on the right hand side of the equation, I will get v, which is a velocity, as a nh upon 2 pi mr. And from equation 8, that is we have derived for the radius of the nth Bohr orbit, which is Rn equal to epsilon 0 n square h square upon pi z m square. If I substitute this value of Rn from equation 8 in the equation v equals to nh upon 2 pi mr, so if I substitute that value of r from equation 8, I will get velocity of the electron in nth Bohr orbit as z e square upon 2 epsilon 0 nh, as equation number 9. So this is the formula for velocity of electron in a nth Bohr orbit, and you can see that the velocity of electron in nth Bohr orbit is inversely proportional to n. That is, as the n increases, that is the number orbit number increases, the velocity of electron goes on decreasing. So velocity is inversely proportional to principal quantum number here. Okay, now let's find the expression for kinetic energy of electron in a nth Bohr's orbit. Now we have classically the formula for kinetic energy as here we will denote the kinetic energy by the letter capital T, do not confuse between period and the kinetic energy. Here we are using the letter T for kinetic energy here. So T equals to 1/2 mv square, and from equation 9 we have already derived the formula for velocity of the electron in nth Bohr orbit, which is Ze square upon 2 epsilon naught nh. Now by substituting these values in the formula for kinetic energy, I will get a kinetic energy of electron in a nth Bohr's orbit as T equals to Z square me power 4 divided by 8 epsilon 0 n square h square as equation number 10. Now let's find the expression for potential energy of electron in a nth Bohr's orbit. Now we already have the formula for potential to find the potential energy. We can find the potential energy by knowing the nature of the force. Here we already have the formula for force, which is the Coulombic force of attraction between positively charged nucleus and negatively charged electron, as F equals to 1 by 4 pi epsilon naught Ze square upon r square. And for the potential energy to find, we have the formula for potential energy as integration of F bar dot dr bar from r to infinity. So here by substituting the values of force in this formula, I will get the potential energy U as integration from r to infinity 1 by 4 pi epsilon naught Ze square by r square. And the now all these things are constant here. 1 by 4 pi epsilon naught is a constant, Ze square is also constant, and integration of 1 by r square will be minus 1 by r. And so I will get, by substituting the limits of the integration in this formula, I will get potential energy U equals to minus 1 by 4 pi epsilon naught Ze square upon r. Okay, now we have the value of r from equation 6 already. So from equation 6 we have the radius of the nth Bohr orbit as epsilon naught n square h square by pi z m square. If I substitute this value of r in the formula for the potential energy, I will get finally the potential energy of the electron as U equals to minus Z square me power 4 divided by 4 epsilon naught square n square h square. So this is the expression for the potential energy of the electron in a nth Bohr's orbit. Now you can observe that the potential energy is negative, and it indicates that the electron moves in a bounded potential. That is, to remove the electron from this bounded potential, you have to supply the energy. That is, the electron is bounded to the nucleus. Now from this formula of total kinetic energy and potential energy, we can find the total energy of electron in nth Bohr's orbit. Now total energy is the sum of kinetic energy and potential energy of the electron. And from equation 10 we have kinetic energy of the electron as a Z square me power 4 upon 8 epsilon 0 square n square h square, and the potential energy from equation 11 as U equals to minus Z square me power 4 upon 4 epsilon naught square n square h square. By substituting these values of kinetic energy and potential energy in the expression of the total energy, if I sum these two, I will get finally equation 12 as the total energy of the electron En in a nth Bohr's orbit as En equals to minus Z square me power 4 upon 8 epsilon naught square n square h square. This is the expression of the total energy of the electron in the nth Bohr orbit. And here negative sign indicates that the motion of the electron is completely bounded to the nucleus. Okay, now here from here we can observe that the energy of the electron in a nth Bohr orbit is inversely proportional to the square of n, that is the square of the principal quantum number. That is, as the energy, as the number orbit number increases, the energy of the total energy of the electron decreases. So it is decreases, and here we can find out that If I substitute the values of mass of the electron, charge of the electron, epsilon 0 permittivity of free space and Planck's constant, all those values in the equation 12, that is in the total energy expression, I will get energy of a nth Bohr orbit as minus 13.6 divided by n square in terms of the electron volt. Now here we are using the unit of energy as electron volt. The conventional or SI unit for the energy is a joule. You can convert the joule into electron volt by dividing by the charge. So 1 joule equals to 1 divided by 1.6 into 10 raised to minus 19 electron volt. And so here we have converted the total energy of the electron in terms of the electron volt, and you get a simplified formula to find the energy of the electron in a nth Bohr orbit as En equals to minus 13.6 by n square electron volt. Now let me calculate the energy for first few orbits. So for n equals to 1, we get E1, that is the energy of the electron, total energy of the electron in the first Bohr orbit as E1 equals to minus 13.6 electron volt. For n equals to 2, I will get minus 13.6 divided by 4, which is E2 equals to minus 3.4 electron volt. Similarly, for n equals to 3, you will find that the total energy of the electron in a n equal to 3 orbit, that is third orbit, is a minus 1.51 electron volt. For n equals to 4, I get E4 as a minus 0.85 electron volt, and you can see that the electron energy is decreasing. So, and the amount by which the energy getting decreased is changing. That is, the difference between E1 and E2 is larger than the difference between E2 and E3, and then the difference between E3 and E4. So difference between the two energy level is getting decreased, and which is picturized here. So here you can observe that the difference between E1 and E2 is much larger than the difference between E2 and E3, and as you go above, as you go on increasing the value of n, the difference between the two level is getting decreased. And the most remarkable thing of this spectra observed here, energy level spectra observed, that the energy levels are discrete. That is, the energy is quantized. The energy level for the electron, any energy is not possible. It cannot randomly take any energy, but the energy level of the electron according to Bohr's theory for the hydrogen atom is quantized. That is, it take a discrete energy values. Classically, the spectra will be continuous because the electron can take any energy, but according to Bohr's theory, it is quantized. As you go on increasing n equals to 1, the density of the energy level goes on increasing. As you can see from this diagram, the energy level becomes more crowded. Initially they are more separated and they gets crowded, and continuum of the energy level formed for higher value of n, that is the principal quantum number. So the two remarkable things are introduced by Bohr's theory, that the energy levels is quantized and angular momentum is quantized, which further introduces the concept of the angular momentum quantization, that is a space quantization. So in Bohr's theory is the first theory which introduce us with this type of quantization of angular momentum and discreteness of the energy levels. Now for this lecture, students have some assignments to solve. So students have to find the velocity of electron in Bohr's first orbit. Now you have to just put the value of n equals to 1 in the formula of velocity of nth Bohr's orbit, which is Ze square by 2 epsilon 0 nh. Second question is, the students have to find the total energy of the energy level corresponding to n equal to 5. That is, you have to find the E5. So you have to just substitute the value of n equals to 5 in the formula for energy, which is a Z square me power 4 upon 8 epsilon 0 square n square h square with negative sign. And the third question is find the energy difference between energy level corresponding to n equal to 3 and n equal to 2. So students here have to find the difference between E3 and E2. So first find the inner E3, that is the energy corresponding to n equals to 3, and then find the E2, which is the energy corresponding to n equal to 2, and find the difference between them. So try to solve these assignments. They will clear your ideas about the Bohr's theory and the expressions that we have seen in this lecture. Now what we have seen in this lecture, let's take highlights of that. We have found out the formula for the radius of the nth Bohr orbit. We have also derived the formula for velocity of electron in nth Bohr orbit, and we have also written an expression for the energy for the electron, that is total energy for the electron in nth Bohr orbit. Now in the upcoming lectures we will get introduced with the origin of line spectrum and different spectral series arises from the electron motion from the two energy levels. So okay, this is for this lecture. Thank you.